Okay, so I think we're ready to get started. So we're very happy today to have Emmanuel Sean visiting us from Lawrence Berkeley National Lab. Emmanuel got his PhD at Princeton University in the Astrophysics department, and then has been a Chamberlain Fellow postdoc, a long-term postdoc at Berkeley since 2017. Is that right? Or is it? Yeah. And today is going to talk to us about the amazing thing. Microwave background and large-scale structure measurements. So Manuel, take it away.
Great. Thank you so much. Thank you for having me. It's great to be able to visit in person and see everyone. Did I need to tell you about some of the research that I've been doing? And the main theme of my research has been, like Kevin said, how to combine observations of the cosmic microwave background, the CMB, that first light from the Big Bang, with observations from the large-scale structure in the universe, that is to say, how matter and galaxies are clumped together in the universe. And specifically, how to use this first light from the Big Bang, the CMB, as a backlight for the large-scale structure, in order to reveal some of the invisible properties of galaxies, much like you would by holding a watermark on a dollar bill in front of the light. So perhaps this made no sense. Hopefully it will by the end of this talk. And in that respect, I wanted to start with some motivation to explain to you why this is something you might want to do at all. And to start, this is my summary of the history of the universe and what we know about cosmology. And so the Big Bang is here all the way on the left, and time moves towards the right, all the way to today, 14 billion years later. Now, there's a lot we know about the history and the composition of the universe, and that we know from a number of different probes. And for the purpose of this talk and most of my research, I'll be focusing only on two classes of probes. The first one, again, is this CMB, cosmic microwave background. So this is light that was emitted only 400,000 years after the Big Bang. And so really what it tells us when you look at an image of the cosmic microwave background, what you see are the initial conditions of the universe. And so this is a map of the cosmic microwave background, and you can see those degree scale hot and cold spots, which tell you about underdense and overdense regions in the early universe. So again, on the one hand, CMB, which tells you about the initial conditions of the universe. And the other class of probes that I've been working on go under the group name of large-scale structure in the universe, how matter and galaxies are clumped together. And so in this illustration, what you can see is every single dot is a galaxy. And as is probably clear from this image, they're not uniformly spread out in space. They're clumped, they're clustered. And so this large-scale structure of the universe tells you about the final conditions of the universe, contrary to the CMB, which tells you about the initial. And in between these two, what you have is 14 billion years of evolution under gravity, where the statistics of these fluctuations, once you evolve them under gravity, should give you the statistics of the galaxies we see today. And so much of the game of cosmology has been to try to map those initial and final conditions, map the statistics of the CMB and the statistics of the large-scale structure. And if you're able to do that, you may have a good model for the universe. Now, again, I just wanted to remind there's many other probes of the history and the evolution of the universe. And I know we have a lot of experts, for example, on supernova in the room. And I don't mean to discard this. These are just the ones that I happen to have. Now, it turns out we happen to have such a good model of the universe that matches the initial and final conditions of the universe. And this model is called the standard model of cosmology. So being able to match observations from so many different observables is a great success. However, this standard model of cosmology relies on components that are not part of the standard model of physics. So dark energy, this mysterious component responsible for the accelerated expansion of the universe. Dark matter, this invisible form of matter, 5 times more abundant than the normal matter that you and I are made of. And inflation or something like it responsible for generating the initial conditions we see in the CMB. And this is one example of looking at astrophysics and looking at the universe as a laboratory for fundamental physics. And this is an example where by looking at gravity, which is hard to do in terrestrial labs, you get to probe beyond standard model physics. And in fact, in the next few years, by combining observations of the CMB and the large-scale structure, we hope to make progress on the question of what is dark energy, so in particular, how much of it is there, how does it evolve with time, which is related to the relationship between density and pressure for dark energy. What is the nature of dark matter? What are its properties like self-interactions or interactions with the rest of the standard model? What is its thermodynamics? And finally, what are the properties of this hypothetical equation? What quantum fields, if any, are responsible for generating it, and at what energy? Now, I wanted to show you another example of how we can use the universe as a lab for fundamental physics. And that's the example of neutrinos. So neutrinos are these particles which are part of the standard model. They're some of the most abundant particles in the universe, almost as abundant as photons. And yet, there's a great deal we don't know about them. So I listed some of the open particle physics questions that remain about the neutrinos. And one that I'll be focusing on is the question of their masses. So we know that neutrinos have a mass. They don't have zero mass. We know that from neutrino oscillation experiments. And we have a lower limit for their mass, but we don't know what the actual value is. And so this is another place where we can use cosmology to answer basically fundamental physics or particle physics question. And again, this is because the universe is a great lab for probing gravity. And gravity lets you weigh the masses of the neutrinos. To tell you briefly how that works, we know that neutrinos are today at least 0.5% of all the matter density in the universe. And so naively, you might think that if you want to be able to detect the masses of those neutrinos, you have to be able to measure this 0.5% effect on matter and its properties. So this seems hard. But actually, we're helped because this 0.5% of the matter happen to not cluster. And as a result, throughout the history of the universe, their gravitational pull on the rest of the matter has slowed down its growth. And so this gravity effect causes a lever arm. And we're no longer talking about a 0.5% effect, but an 8 times larger effect, so a 4% effect on the large-scale structure. And so what this means is if you want to detect the masses of the neutrinos using cosmology, you don't need to measure the large-scale structure to 0.5%. It's good enough to measure it to 4%. And now that's within the reach of upcoming experiments. To show you what the effect looks like, these are two simulations of the large-scale structure. What you see in color is the matter density field. So red is overdense and blue is underdense. And you're comparing here the massless neutrino case and the case where neutrinos actually have a mass, which is the truth. And if you look at those two different simulations, they look almost identical, except you see a lot more blue here than there. And that means the structure on small scale, those small dark matter halos have been erased by neutrinos. And this is the 4% effect that we're after. In fact, our forecasts show that by combining CMB and large-scale structure, we expect to detect the masses of those neutrinos at least 3 sigma in the minimum case. So this is an exciting prospect for cosmology.
So when you say detect neutrinos, you mean an absolute mass scale? Mm-hmm. And then use oscillations to find the masses of all the species, or
right. So the neutrino oscillations tell us about the differences between the mass squared, but it doesn't tell us about the overall mass. Here, what we're measuring is the sum of the masses of the 3 species. And so, if you combine that information with the neutrino information, then you have the mass of each of them. And so the statement here is that we'll be able to make a 3 sigma detection of the sum of those masses. So that's pretty exciting. And so how do we do all this? How do we learn about neutrinos, but also dark energy, dark matter identification using the cosmic microwave background and the large-scale structure? One way to do it, which is the way I've been pursuing, is the following. So I told you at the start that the CMB tells us about the initial conditions of the universe. And that's mostly true. That's true for all of the CMB photons that have traveled since the time the CMB was emitted all the way to us today, 40 billion years later. But actually, this path is not the path of all CMB photons, because along the way, the path of CMB dancing photons gets deflected by the gravitational pull from individual galaxies and from the large-scale structure universe. And so this effect of massive objects deflecting the path of light is called gravitational lensing. And loosely, I'll call this one of the shadows of the large-scale structure on the cosmic microwave background. And another important effect is that some of the CMB photons, about 6% of them, as they travel towards us, eventually will hit a free electron around a galaxy or galaxy cluster and get scattered. And this scattering imprints another property of the large-scale structure on the CMB. So while lensing imprints the property which is mass, visible and invisible, the scattering effect imprints tells you where the electrons are, so it tells you about the gas distribution in the large-scale structure. And so these two properties, the total mass around galaxies and the total gas around galaxies, are actually very hard or almost impossible to observe in any other way. I'll tell you a bit more about this. And so these are just two ways to use the cosmic microwave background as a backlight for the large-scale structure, backlight for those galaxies, in order to reveal these invisible properties. This is what I'll be mostly talking about today.
If you want, I think you can get rid of this transcription.
Thank you.
Yeah.
So why is now a good time to pursue these observations? The answer is twofold. First, the fact that we have a number of high resolution and high sensitivity CMB experiments that are coming online and that are going to much improve our ability to measure the cosmic microwave background and therefore these shadows. And so a number of these experiments will be very familiar to people in the room. One is Advanced ACT, the Atacama Cosmology Telescope, of which part of along with other people here, which will be succeeded soon by the Simons Observatory, for which I'm currently one of the pipeline co-leads for CMB lensing and now kinematic resolution events. And finally, by the end of the decade, we should have the start of cosmic microwave background stage 4, yet the successor of Simons Observatory. And so this means there's a lot of data coming online, a lot of new measurements of the cosmic microwave background that are really going to improve resolution and sensitivity, which are exactly what we need to measure these shadows. Now, the second reason now is a good time to pursue those measurements is that we're also about to get gigantic large-scale structure surveys. And so the first one I wanted to mention, which has started already and almost has its first year of data, is DESI, the Dark Energy Spectroscopic Instrument. And so this survey is going to measure the 3D positions in space of galaxies of tens of millions of galaxies. The Vera Rubin Observatory, which will come online very soon, will measure not the 3D but the 2D positions of galaxies, but instead of tens of millions, it will do it for billions of galaxies. And the reason why these numbers matter is that the number of galaxies in your catalog really is your currency in terms of statistical signal to noise. So your statistical power is how many galaxies you have. And these numbers, tens of millions in 3D, billions in 2D, really blow out of the water anything we have at the moment. And finally, I just wanted to highlight this satellite, SphereX, that has been approved for launch recently. And this is a very different system compared to those. It's actually a very small mirror, something like 20 centimeters, but with a very wide field of view that's going to measure the clustering of the galaxies on the larger scales to learn about inflation. So hopefully I convinced you that now was an interesting time to think about these questions. And before going deeper into the talk, I just wanted to mention some of my research that I won't tell you more in detail, but I'm happy to talk about. So I worked on galaxy surveys, in particular the the theory of the large-scale structure, so those effective field theory for gravity, and some of the systematics of galaxy surveys. I've worked a lot on the cosmic microwave background and recently on this new observable called intensity mapping, which perhaps one day will be the best of both worlds. But what's most specific about my research is trying to bridge the gap between these different observables. And so how to use measurements of CMB lensing to improve the systematics of galaxy lensing. How to use methods from perturbation theory and the large-scale structure to enable the first detection of a correlation between CMB lensing and intensity mapping. How to port methods from the CMB to measure lensing of intensity mapping, and how to compare intensity mapping and galaxy surveys. But today what I'll focus on are these two directions, gravitational lensing of the CMB, or shadows of the mass, and baryon mapping, or shadows of the gas, how to reveal the gas.
So sorry for interrupting you. So these three sigma determination of the two, what's the time scale for that?
So this, for this 3 sigma, what you will need is basically dizzy, some of Rabin, so we're thinking mid-2020s, and you will need CMB from Simon's Observatory. So coming fairly soon. Sorry?
End of the decade.
Oh, yeah, hopefully. Now, of course, all these timelines always tend to shift as time goes by and they turn away. But I think that's a realistic estimate, yeah. So this will be the outline. I'll tell you first about those mass shadows, and those gas shadows, and then I'll tell you a bit about future directions. So let's get started. Mass shadows, and in particular, what I want to tell you here is how understanding a deep analogy between lensing of the cosmic microwave background and lensing of the galaxies actually lets you improve your CMB lensing methods. So here's a quick overview of how CMB lensing works. So again, as the CMB photons travel all the way to us, they don't follow a straight line, or rather, they follow a straight line in curved space due to the gravitational pull of galaxies in the large-scale structure. This results in deflections in the cosmic microwave background that are very small, only arc minutes in size, which you remember it is much smaller than the degree scale of the CMB blobs that I showed you at the start. But those small deflections are actually coherent on the same degree scale, and this is what will allow us to detect them. Gravitational lensing conserves surface brightness. What this means is that it's only a remapping. So the CMB temperature that you observe here is the CMB temperature you would have observed there, where the difference between here and there is this deflection field. And this deflection field tells you directly about the gravitational potential of your galaxies and therefore the mass. And so when you measure these deflections, what you're measuring is the projected mass density field between the CMB and us. And so if you turn this cube and you look at the projection, you get something like this. And so this map of the density deflection, or the convergence, as we like to parameterize it, really is a map of the matter density field all the way between us and the CMB. Now, what does this do to the CMB? What's the observable here? So let me show this to you. Here's a simulation of the unlensed CMB. The CMB you would see if there were no deflections. And this is an image of the lensed CMB. And so if I flip between the two, what you see is the difference between these two is fairly small. Again, there are those arc-minute deflection, but they're coherent on larger scales, on degree scales, the scales of these blobs, basically. And so this is what enables us to detect it. In practice, the way we do this is by exploiting the fact that while the unlensed CMB would otherwise be statistically isotropic, meaning its statistical properties are the same in this part of the sky or that part of the sky, lensing breaks this, because if you have a massive object here and not there, this will no longer be statistically isotropic. And mathematically, what this means is that the small and the large scale Fourier modes, the small and large scale fluctuations in this map become correlated. And so naturally, to detect this effect, we look at the covariance, the correlation between small and large scale modes. And so this is something that you might hear in CMB lensing world as the quadratic estimator. It's really just multiplying small and large scale modes to measure this covariance. Okay, so this is CMB lensing and how it works, how we detect it. I just wanted to explain why it's important. And so what I have here is a table of the various science cases and parameters that an experiment like Simon's Observatory or CMBS4 aims to measure. And I don't mean for you to read all of these numbers. All I wanted to do was to highlight the science cases for which CMB lensing is key. And so as you can see, CMB lensing is key for most of the science goals of these experiments. Learning about inflation and the primordial fluctuation in the universe, learning about the number of neutrinos in the universe, but also potential light particles in the early universe, measuring the masses of the neutrinos, properties of dark energy, and more I'll tell you soon about galaxy evolution. So CMB lensing is crucial for these experiments, and it turns out these experiments will detect it at very high significance. So we're talking 100 sigma and 400 sigma, so very high precision measurements of the CMB lensing from the experiments. So this all sounds great. Let's just do CMB lensing then. However, unfortunately, there's one key challenge to making those precise measurements of CMB lensing. And this challenge is that of extragalactic foregrounds. What this means is these are things that are not in our Milky Way galaxy, but are in between us and the CMB, and also get imprinted on our maps. So what we want is to observe the cosmic microwave background, but when we look at microwave frequencies, what we also see is those different effects. Thermal and kinematic Sunyaev-Zoltowicz effects, I'll tell you a lot more about them in a moment. The cosmic infrared background, basically just thermal emission from distant galaxies, and point sources, galaxies that emit in radio. And what this does is that all this gets added to your map. And if you don't do anything about it, if you don't do anything to clean these foregrounds, what you get is the following fractional bias on the power spectrum, CL, of that lensing convergence scale. So this is the fractional error, fractional bias on your lensing measurement as a function of scales. The scale dependence here is not very important. What I want you to see is compare this gray band, which is the statistical uncertainty for an experiment like Simon's Observatory, with the actual size of the bias for the standard quadratic estimator. So you would want the bias to be 0 within that statistical uncertainty. And instead, what you see is it's a very large, extremely significant bias. So this is what happens if you don't do anything about the foregrounds. And what this means is that basically, if this is the CMB lensing measurement you're going to produce, you might as well throw it out. It's completely wrong. So that's the key challenge, and one on which you can actually make a lot of progress by understanding a very simple analogy between how lensing acts on the cosmic microwave background and how it acts on the images of galaxies. And so you may have heard of the lensing of galaxies. And the way it works is that when you have an image of a galaxy, on average, it might be round. But if its image is being lensed, it might get magnified, increased in size. So this is what you'll see. Or it might get sheared, so squeezed in a certain direction. And so in galaxy lensing world, we always talk about magnification and shear as the observables for galaxy lensing. And so this may sound quite different from the picture I presented for CMB lensing, which was coupling between small and large scale nodes and those quadratic estimators. But actually, it turns out under the hood, these two measurements are very analogous. And to understand the analogy, we can think as follows. If you remember in the CMB map, I had those hot and cold spots. And these are the things that on average are round. But to see it, what you can do is take a small patch of your CMB map and Fourier transform it. Those hot and cold spots that are on average round turn into acoustic rays. And so now you have a quantity which is analogous to a galaxy image, something that on average is round. And when your patch is magnified in Fourier space, those rings get squished. And if the patch is sheared in Fourier space, your image gets compressed. And so it turns out what the standard estimator for CMB lensing, that quadratic estimator that I told you about, does is the same as galaxy lensing. Under the hood, it is measuring this magnification and those shear effects, which are really a monopole and a quadrupole distortion of that 2D Fourier transform. Now, okay, this maybe was complicated. What's the point of this? The point of noticing this is that if the standard CMB lensing estimator measures the combination of magnification and shear, once you understand this, you can actually split it into a magnification only and a shear only CMB lensing estimators. And I think our breakthrough here was to understand why that would help. So let me show you why that would help. And the reason it does is because the symmetries of lensing and foregrounds are actually different. So for lensing, as I just said, the effect is a monopole, magnification, and a quadrupole, shear. But instead, if you look at foregrounds and what they look like, these are mostly point-like objects, or objects on average are spherical, added to your map. And so the effect on the map is only a monopole, not a quadrupole. And so intuitively, once you split the CMB lensing estimator into a magnification only and a shear only estimator, you would expect that foregrounds would only bias the monopole, the magnification, and not the shear part. And so this, I think, was the key intuition. And so to make sure this works, we tested it on these realistic simulations of foregrounds. And so you've seen this plot before. This is the large bias on the standard quadratic estimator due to these foregrounds.
I have a quick question.
Oh, yes.
Do you expect with the lensing, do you expect the monopole and the shear to be correlated in any way, or are they potentially uncorrelated?
Right, it's a really good question. So the cause of the magnification and the shear is the same matter density field.
Right, yeah.
And so there are two observables of the same effect, but the observables themselves have pretty much independent noise.
Okay.
So it's the same as if in galaxy surveys you can measure the shear, and then you can measure the magnification. They should agree, but they're still two independent observables.
Okay. I was just wondering if basically you have to, yeah, I get what you're saying. Basically look at the shear, and then that's your signal of the lensing. I'm wondering if you have to throw away the monopole or if you can still use it.
Yeah, that's a really good question. And the answer is there's about half and half of the information in the shear and the magnification. And so if you're going to throw out the monopole or the magnification, at face value, you think you've lost half of the information. But it turns out it's not quite the case. Maybe I'll show you right now. So again, you've seen this very large bias from the standard quadratic estimator. If instead you look at only the magnification part, you find an even larger bias. And that's, again, this intuition that a lot of the bias should be in magnification. And when you look at the shear only part in blue, basically the bias is gone. And so again, if you throw out the magnification part, you lost half of the information. But because the shear is so effective at knowing the foregrounds, you can actually include smaller scale data in your shear measurement. And the information content in these maps as a function of how small in scale you go increases super fast. And so by using only the shear but down to smaller scales, you actually have higher signal to noise than with shear and magnification originally. So you have thrown out the magnification information, but you have gained sufficiently more shear to offset that. And so that's kind of the key result is that it nulls those biases. And because it does it so well, it lets you go to smaller scales and therefore even increase the signal to noise. So it's a lower bias, lower noise measurement. I think there were two questions. And first.
My question is this bias estimated using temperature only or?
Right, yes, a very good question. So these are biases from temperature measurements only. And so they're very relevant for an experiment like Simon's Observatory, where most of the lensing comes from temperature. As you mentioned, there's also measurements of polarization available. And in fact, for an experiment like CMB stage 4, most of the lensing information will come from polarization. And so the question of extracting foreground biases in polarization is an important one, and one for which the answer might be different. And actually, this is a project that I've been pursuing with Mary Smilia, another postdoc at Berkeley, to estimate those extragalactic foreground biases in polarization. And we're not done yet, but it looks optimistic in that the foregrounds are much simpler in polarization than they are in temperature, the extragalactic foregrounds.
So I have one question. Is this lensing an integrated effect all the way to the CMB, or is it possible you would have multiple lensing events along the way? And if so, how do you rule them out?
Right. So yeah. So when you measure CMB lensing, you are measuring the sum of all the deflections of the light as it traveled between the CMB and us. And so you're actually measuring typically the combination of multiple lensing deflection events. And so right, you're reconstructing only one 2D map, which takes into account the sum of these deflection events.
All right, thank you.
That was a question.
There's a small increase in the bias between, say, 800 and 1,000, and then it's less around 200 and more around and less around 2,000 again.
Mhm.
Is that understood? I mean, it's a log scale, so I guess it's significant. And is that an effect more of the the kind of experimental measurement you're simulating, or something with the estimator?
Right, it's a good question. So I should say, yeah, this axis is linear, but that one is not.
Right.
And yes, so this decomposition in shear and magnification that I presented here actually is exact in the regime where, just like for galaxy lensing, you have very small galaxies that are lensed with a slowly varying lensing field. And so that regime means you are looking at very small scales in your map, CMB or galaxies, to reconstruct large-scale lensing. And so in this plot, it's mostly those large-scale lenses. And so this analogy, shear magnification, actually is less and less exact as you move to the small scales. And there is a generalization of it that actually does better and gets rid of this effect. We presented it in this paper. I'm not showing it in the talk. And then there's ways to go even further.
And then the fact that the bias seems to decrease again at like maybe 2,000 on this plot, should we read anything into that, or is that just?
Yeah, it becomes. So are you thinking about the green or red curve, or
The blue even.
the blue?
Yeah.
Yeah, it's at this stage it becomes somewhat coincidental.
Okay.
The exact thing. But yeah, so we actually can do better than those shear and magnification, and these are another monopole decomposition that's a bit more exact, but slightly different from the galaxy lensing one. And in fact, there's ways to do even better than this. So this was an example of leveraging the difference in symmetries between lensing and foregrounds to get rid of foregrounds. If you're willing to assume a little bit more about your foregrounds, then you can do that better. And this is called bias hardening. And so I just want to highlight the work of Noah Saylor, who's a grad student at Berkeley, and Omar Darwish, who's a grad student in Cambridge, who showed that those methods can actually do even better than what I showed you with shear magnification. I also wanted to highlight the work of Nishant Mishra, who was a student at Berkeley, an undergrad student at Berkeley, and did his first paper on this. So this was his first research project that he led, and did the first calculation of another bias to lensing, which is the fact that not only there are foregrounds, but because the foregrounds are far away, they are themselves lensed. So this is another bias that we computed for the first time. And then this is the work of Abhishek Maniyar, a postdoc, who extended those methods to the case of intensity mapping this new probe of the universe. So very interesting stuff, and I think quite a bit more to be done on this topic. So this is all I wanted to say about those mass shadows and this lensing. And so if there's any question on this, please go ahead. Otherwise, I'll move on to those gas shadows.
Well, just one on the mass shadow. So if you're integrating lensing all the way to the CMB, would these information be able to rule in or out some people's arguments that there are large scale anisotropies in the large scale structure, like, like the dipole and so forth? Would you pick up differences?
Right, that's a good question. And so you are indeed probing all the mass distribution between us and the CMB. And the way it is weighted means that you actually get a lot of information between us, so redshift 0, and something like redshift 2 or more. And so things that might be either at the time of the CMB are a little bit too far for you to probe with the CMB density. And things that might be very local to the Milky Way's environment are a bit too local. So in that sense, the CMB densing is more a probe of the large scale structure in between. I hope that helps.
Right, but if there were any huge voids, I've heard people argue that there are huge voids here and there and so forth, and that they argue against isotropy and homogeneity. It seems that your data may be useful in resolving some of those issues.
Yep, I agree. Cool, thank you. So I'll move on to those gas shadows, or how to localize the baryons, meaning the ordinary matter around galaxies. And so you might think, why care about the baryons? These are the ordinary matter. Should we focus on the dark matter and dark energy? And it turns out there's a lot we don't know about the ordinary matter, and we need to know this to then answer questions about dark matter. And so you may have seen those little images of galaxies. This is a galaxy the way it typically looks like. But what you may not know is that around every tiny little galaxy in the universe, there's actually a giant gas cloud that you cannot see, and that we're able to reveal through their shadows on the scene. So again, why care about? Why care about this gas? And the answer is twofold. You should care about this gas if you want to learn about galaxy formation or cosmology. Let me explain. Here's a simulation, industry simulation. It's a hydrodynamical cosmological simulation. What you see here in blue are clumps of dark matter halos in which galaxies and galaxy clusters live. But if instead of looking at the dark matter in blue, you start looking at the ordinary matter, mostly in the form of gas, something you'll start to see in red and green. What you find is that the gas does not completely follow dark matter, because there's all these explosions, all these fireworks going on. And these fireworks have to do with supernova, so explosions of massive stars, and accretion onto supermassive black holes, which injects energy into the gas. And because of all these fireworks, what happens is that the gas, and so most of the ordinary matter, gets blown out away from the dark matter. This is called feedback, because it's a negative feedback in star formation. Once you blow out the gas, it's harder for it to cool and form stars. And it turns out the amplitude of this feedback is one of the key unknown in galaxy formation. At the same time, what happens is that when this gas gets pushed out away from the center of halos, the gas around here ends up being too diffuse and too cold, and therefore too faint to see directly in emission. And so this gas here is actually invisible. And this problem has been called the missing baryon problem. The fact that if you just count the stars, there's much less ordinary matter than you'd expect. And that's because most of the ordinary matter is in the gas. And none of that gas is too far to diffuse for you to detect. And so if you could localize that gas, you could see how far it is, how energetic it is. That would tell you about how much energy has been injected in the gas to those feedback effects. And so you would answer this key question in galaxy formation. What's the amplitude of this feedback? But in fact, it's also an important question for cosmology. And the reason is fairly simple. Upcoming large-scale structure experiments are going to give us maps of the total matter in the universe, so dark matter plus visible, that are basically percent precision maps. But it's impossible to analyze this percent precision data if you don't know where the ordinary matter, which is 15% of the total matter, is. So that's fairly straightforward. If you want to analyze this percent precision data, you need to first figure out where 15% of the matter is, where those missing baryons are. And in fact, this is not just a problem for future large-scale structure experiments. Here's one existing measurement. This is mass density profile measured through galaxy lensing around galaxies as a function of distance from the galaxy you're considering. So please don't be alarmed by the weird S shape. This has to do with how this was plotted. But what I want you to notice is the difference between this red curve, which is what you would expect the mass profile to be if the baryons or the ordinary matter follow the dark matter. And instead, the measurements are here in green with arrow bars. And so you can see there's a clear tension between the measurements and the data. Now, if the baryons don't follow the dark matter, what do they do? At most, what you can do is blow them so far out that they're completely gone. And so if you get rid completely of the baryons, you have removed 50% of the matter in the universe, and what you get is this dashed curve. So you cannot really do more than that. And the reality should be somewhere in between. And so what you can see is that while this might not solve the whole tension, it might be a significant part of it, one that you definitely need to get under control. And so the plan here is to answer this question and say, where is reality between those two curves by using CMB and those gas shadows?
I have a question.
Yes.
This part. Definitely reconstruction of the uncertainty should depend on the distance very effectively.
Mhm.
In your arrow bars, these are Gaussian statistics probably, or something. It looks pretty symmetric. What are the uncertainties in the measurement itself due to systematic errors?
Mhm.
Because if you go further away, lensing will become the lensing parameters become much less determined.
Yes, that's a good question. So the way this measurement is done is you have galaxies, and within rings of at a certain distance around them, you look at the shapes of background galaxies and how sheared they are by this massive galaxy. So here, in terms of statistical uncertainty, it's mostly about in a certain ring, how many distant galaxies you have. And so if say your ring had constant width, as you go farther out, you have more and more area, so more and more galaxies. So the statistical error doesn't necessarily have to
No,
be.
but the systematic error.
Right.
It looks like your thing is a little bit tilted or a little bit disturbed, and your arrows don't reflect any of the
Right. So there's a
thing.
number of statistical systematic errors. Some of them actually get worse as you get closer because of confusion between the light of galaxies and the background ones. What I should say, and I did not explain in detail, is that what is actually plotted here is some power of the distance times the actual observable of lensing, which is the mean mass density at that radius minus the mean mass density within that radius, because that's the most direct observable, and that's what causes this shape. And then the last thing I should say is because when you have a measurement in real space, in cosmology, often the error bars end up being somewhat correlated to this sample variance. So that correlates a bit with error bars.
Mm-hmm.
Maybe it's time for me to explain what I actually mean by gas shadows. And I use this word a lot in the talk, but this is what this is actually. Gas shadows here are the so-called Sunyaev-Zadovich effects. And what they are is the change in the energy of CMB photons as they bounce off moving electrons and finally reach your telescope. And so this effect physically is really just a Doppler effect. You have a photon bouncing off a moving mirror. So it's like a tennis ball bouncing off a moving racket. The racket is going towards you, the tennis ball gets accelerated. And so similarly, if the electron is moving towards you, the CMB photon gains energy. If the electron or the tennis racket is moving away from you, the CMB photon loses energy. So Sunyaev-Zadovich effect is really just a Doppler effect due to the motion of the electrons. And it turns out there's two sources of motion for these electrons. One is the fact that these electrons are in a hot and as gas, hot plasma, and so they have thermal motion. And so this is called the thermal Sunyaev-Zadovich effect, because it's a Doppler effect, it tells you about the thermal velocity. And so it tells you about the temperature of the gas. And it also tells you about the gas density, because simply put, if you had no gas, you have no electrons, there will be no effect. The second source of motion for the electron is the fact that the whole cloud of gas might be moving towards you or away from you. And so this is called the kinematic Sunyaev-Zadovich effect. It's due to the bulk motion of that gas. And so naturally it tells you about the bulk velocity of the gas. And again, it's linear in the gas density, because if you had no gas, you would have no effect. So these are actually two distinct types of shadows on the cosmic microwave background that you can measure separately. One will tell you about the gas density, so where the gas is. The other one will tell you about density times temperature, or pressure, or thermal energy of your gas. And so if you can measure these two, you actually have a probe not just of where the gas is, but of its thermodynamics.
Is that the only way that the silicon can change energy? There are no scattering effects.
Right.
I mean, you say it's only Doppler, right? But I mean, even can there be exchange of energy when it scatters? Or?
Mhm. Yes. So so this is a Thomson scattering, but on a moving target.
Okay.
There's an effect of Thomson scattering on a non-moving target, and that one is yet another imprint on the CMP. It turns out it's a bit of a smaller effect, so harder to detect, but it's definitely there. And in fact, there's a lot more shadows on the CMP of galaxies from a combination of all these scattering, all these motions, and lensing, and higher order effect where you multiply them all. So yeah, completely right. Because of time, I won't tell you too much about this, but the kinematic and the thermal SZ are unique probes of the gas. They probe it in ways that are really hard to do in any other way. So if you're interested, please ask me. So let's start with the thermal SZ, and let's look at what it actually looks like. And so what you can do is you can find a galaxy in an optical catalog, and then you can look at your CMB map at the position of this galaxy to see what the shadow looks like. And so in this cosmic microwave background map, this whole image of the galaxy actually fits within the central pixel right here. And this white circle here tells you the resolution of our CMB map. And this outer white circle tells you how far the dark matter is expected to expand around this galaxy. And if you look at this image, what you see is basically nothing, just noise, because that signal is way too small from a single galaxy to be seen in our eyes. And so when that happens, one way to solve this problem is to use the fact that we have large catalogs of galaxies. And so you can average, you can stack the signal from many, many galaxies, something like 400,000. So this is what happens as you add more and more and more galaxies. So I can play it again. But as you add more and more galaxies, you get independent realization of the noise. And finally, the noise averages down, you start to see this dark shadow of the gas. And so this is the thermal Sunya exhibit. And as you can see, the gas shadow is way more extended than the galaxy, which again fits within the very central pixel of this map. So that was the thermal SZ effect. What about the kinematic SZ? Well, for that one, there's a challenge is that the dependence here in the bond velocity means that for some of the objects moving towards you, it's a positive effect. And for the objects moving away from you, it's a negative effect. So if you simply average or stack like I just did, that effect cancels out. And so to detect this effect, you have to work a bit harder. And the method that I sort of implemented for one of the first times is to use an external handle on the velocity of the galaxies to avoid this cancellation. So in this case, the external handle on the velocity comes from this thing called velocity reconstruction. And really, it's a consequence of mass conservation. It just says that if you have mass conservation and you have more mass somewhere, it's because stuff has been moving there. And so there's a relationship between velocity and density. Again, if you have more mass here, so the stuff has been moving there. And this may seem very crude, but it's actually a very good handle on the velocities of the galaxies. And so using this method, we can actually evaluate on many, many galaxies, hundreds of thousands of them, where we think they should be moving. And so apologize for all the colors. You are here. This white box is a 3D box of the universe around us. And you are here. Every dot is a galaxy in our bus sample of 400,000 galaxies. And color-coded in blue and red is whether they're moving away or towards us based on this reconstruction. And so there, having the 3D information for the galaxies is crucial. And once you have this, you can perform the same stack as before, but avoid that cancellation due to the change in sign. And so when you do this, is what you get. Again, the gas shadow from thermal SZ, and this perhaps uninspiring yellow blob at the center is actually the highest precision measurements of the kinematic SZ effect today. So the consequence, as you can see, is that the gas here extends much farther out than the galaxy, but in fact also much farther out than the dark matter profile, the outer white circle. And so using the CMB, we're able to resolve those gas profiles, and we're able to make statements like this one, which are really cool.
So that statement about the dark matter, that's just the, how do you?
Right. So that statement actually comes entirely from the KSZ, because there you have a clean measurement of density alone without temperature information. And you may not see it on this image, but our actual measurement is an azimuth average of this. And there you can actually compare dark matter and gas profile and see that the statement is super significant.
Get the dark matter profile from.
Oh, the same galaxies have been measured with galaxy lensing and CMB lensing. And so we have dark matter profiles this way, or total matter.
The gas is outside dark matter.
So that circle here is actually the viral radius. And we find gas out to multiple viral radii. That's cool, thanks.
That's really cool.
Cool, thank you. And so what do we do with those measurements of the gas? I told you about that lensing tension earlier. And so now that we actually have the measurement of the gas, we can show where reality is between baryons follows dark matter and baryons are completely gone. And the answer is there. And so as you can see, the effect of knowing where the baryons are does not completely solve the tension, but it's a big part of it, maybe half of it. And so it's definitely something you need to know if you want to be able to do those measurements for this. Yes.
Was also surprised there's no scale on this information. It is well understood how to generate in the
Oh, right. Yeah, so you're wondering if there's a degeneracy between defective baryons and defective neutrinos. Right, yeah, that's a very good question. And in this case, the effect of baryons is mostly on the scale of individual halos, something like megaparsec scale, for example. Whereas the suppression of power due to neutrinos, when we say it's on small scales, it's actually all scales smaller than 100 megaparsec roughly. And so there is a broad range of scale where you see, if you want, only the neutrino suppression in other baryons and then both of them. But it's interesting to have the baryons sorted out, because then that means you're able to use smaller and smaller scales in your data to probe the neutrinos. Cool, thanks. And I'll just mention there's much more to be done on this topic. I just wanted to highlight the work of Stéphanie Amodeo, who's now a postdoc in Strasbourg in France, and Emily Moser, a student in Cornell, as well as many other collaborators on learning not just about galaxy formation, but the impact on lensing of having measured the baryons. And the one thing I'm really excited about right now and in the next few years in this research direction is DESI, the dark energy spectroscopic instrument. And these are images that I took while I was helping with the commissioning in January 2020. And by now we have about more than 1 year of DESI data. And this is really already an order of magnitude more than all the previous spectroscopic surveys. And so this will be really, really useful for solving the baryonic uncertainty for lensing that I talked about and learning about galaxy formation. So I'll stop there. I've told you about those mass shadows and those gas shadows, which are useful for solving the baryonic uncertainty and learning about galaxy formation. And maybe very quickly, I'll tell you about the future of this research and where I see it going. Oops. And I think there's a lot to be done on the direction of neutrino masses, but also dark energy inflation, dark matter, and galaxy formation in the next few years using those data sets. And I think on the shortest timescales will be those measurements of thermal SE and KSE using DESI and CMB data from the Atacama Smart Telescope, Simon Observatory, CMBS4. So I think this will really be a game changer. And then on a slightly longer time scale, will be the measurement of the neutrino masses. And for this, a number of key systematics in the galaxy and CMB lensing needs to be controlled. And this is a place where new methods for CMB and galaxy lensing will be useful. And finally, much longer time scale, maybe 2030s, once CMB and galaxy catalogs are done. Things like intensity mapping has a very powerful potential for cosmology. So I'll stop there. Thanks for your attention, and I'll be happy to take more questions.
Thank you. Are there questions people have for Emmanuel? We had several questions along the way.
So I did have, first of all, thank you for that talk, very clear and illuminating. And I was really impressed by the way you were using the distribution of galaxies to get at velocity information. Yeah, because that's like not having to get spectra of all those things so that you know the velocity, and then being able to use the distribution is a really interesting idea. And like if you go back one, like what I was struck by is, you know, if you had, without showing me that this works, and I'm actually curious to see more like some of the papers that show that this really does work. Like for example, the figure on the left, you look at all those galaxies and the knots, and then we have this vague notion that those galaxies are virialized. So their distribution on the sky or within space is pretty much uncorrelated with their actual velocity. But what I think is clear to me is that you're using all of the information outside of the virialized clumps, and then that's what's able to, because those haven't been virialized yet, they're just now falling into the regions.
Yeah, that's a really good point, because indeed, once you have a halo or a cluster of galaxies, galaxies are moving around that cluster with random velocities. And so the motion within the cluster, you basically have no information on that from the outside, like you said, because they're virialized. And what helps us here is a couple of things. One, the galaxies in our catalog are typically centrals in that halo. And so, or in that galaxy group or cluster. And so that component of virial motion might be small. But that one is a motion we're definitely not capturing with our reconstruction. And here it's not a bias, it's just a loss of signal strength. But the other thing that helps us is that, so instead we're looking at the motion, if you want, of that whole cluster. And a lot of the velocities come from our coherent on very large scales. So while, you know,
so even within clusters, there's motion, the clusters are falling into each other.
Right, and that's the motion I care most about here, because the gas is sort of attached to the cluster and stuff. And so, yeah, if you look at the hydrocene, you look what's the RMS velocity of these clusters, you find that it's very close to what you get if you had smoothed out that matter density field on scales of 50 megaparsec. And so while the density field coherence length might be small, the velocity field is coherent on much, much larger scales. And this has to do, you can sort of understand it with this equation in Fourier space. Those operators are factors of k that boost the lower scales. Oops, I was telling my alarm to stop talking. But I'll keep talking anyway. And that helps us a lot, because it means linear theory is good enough to reconstruct the velocities. And when I say good enough, it's something we've actually checked with simulation. The correlation coefficient between true and reconstructed velocity per object is something like 70%. And not having 100% in our estimator means we're losing some signal to noise, not being biased.
And you don't need the absolute velocity, you just need the gradient in the density, which you're using the galaxies as tracers of the density.
That's
you don't know that true density.
That's right. And actually, it's sort of something you see here is that each dot is a galaxy, but you see the blob of coherent velocities actually super large. This is like 100 megaparsecs, it's like 400. So these are super, super large scales.
I was noticing all the white in between. That's what was partially giving me a clue that this was also going on in terms of, like, that's probably the virialized stuff there that's white. Or is that just like stuff that's at zero velocity?
So that's saying on the very large scales where stuff is moving like this, if you want, the white would be kind of this patch here.
Yeah.
That's right. Thanks.
Well, I think our hour is up. So I can see that Bill has a question, but I think we'll let the people in the room go, and then Bill, you can ask your question in a minute. So So Emmanuel is around for tomorrow and a little bit on Wednesday. So if you would like to have a conversation with them, just get in touch with me and I can get that set up. Otherwise, we're going to be going for dinner tonight and tomorrow and lunch tomorrow. So if you're interested in joining one of those events, also let me know. So let's thank Emmanuel again and thanks all for coming. Bill, did you want to ask a question or do you want to?
Well,
come
just
over?
quickly, Emmanuel, very nice talk. Have you found any major surprises so far?
Yeah, that's a good question. So I think it depends a bit on your perspective. So I think a lot of people who work on cosmological hydrodynamical simulations expected the gas to be this far out. And so I think in their perspective, this was not surprising. But I think for a lot of other people, this was a surprise that the gas would be so far out, several times the Vero radius.
I see.
That's one thing. Another thing maybe that was surprising is when you look at that shadow of the gas in that dark blob, something that I didn't point out is there's actually a light blob at the very center. And that one is actually dust emission that fills the shadow. So this is not the shadow I'm interested in. This is thermal dust emission from the galaxies. And I think this was surprising to people because those galaxies that we've been looking at have been selected to have no dust. And this matters to a lot of the other applications they're used for. So redshift space distortion, for example. And so having found that dust in the galaxy, I think went a bit against the common knowledge before this.
Very cool. Thank you.
Thanks.
Thanks, everybody.